Hello, and good morning, everyone. Welcome to this presentation. Uh, Thanks so much for joining us. Uh, in this presentation, we want to solve a problem um, under one problem under this course, the numerical linear algebra and approximations. And we are going to solve a paper from Mulungu University. Okay. From this exam, which they had on the 11th of June, 2024. Okay, so we are interested in approximation. Okay, finding the percentage error, maximum percentage error. That is our interest. Okay, so let's look at the question. Please don't forget to subscribe. Okay, don't forget to subscribe, share with your friend. If you're a university student, could be doing your master's, and you do maybe want to see how best we can find this problem, please enjoy as we present. Also, share with your friends. Okay, let's see. Okay, there is this question. I hope you're able to see it. Okay, so we are saying if u is defined as 4x squared y to the power 3 divided by 4z to the power 4, and the errors in x, y, and z 0.001, we need to approximate, okay, the percentage maximum error in the function u when x is equal to y, y is equal to z, and everything there is equal to 1. That's what we want to do. Okay, that's what we want to do. So how best do we handle that? Okay, let me bring my board. Okay. Here we go. We have our solution. So we have that u is equal to 4x squared y to the power 3, everything divided by z to the power 4. And we are saying the errors in x, y, and z be 0.001. Now we need to compute the percentage maximum error in u when x, so we need the percentage maximum error when x is equal to y and this is equal to z, which is equal to 1. Okay. So to get the maximum error of this function, we need to differentiate. Okay, we need to come up with partial derivatives. So we are going to say uh, du, the derivative of u, will be equal to partial u divided by partial x with respect to x dx plus partial u, then partial y with respect to y, then plus partial u divided by partial z with respect to z. Okay, so now we need to determine these partial derivatives, these three. So this implies therefore that the partial u to x, what are we going to differentiate? We are going to differentiate to u partially with respect to x, considering y and z as our constants. Okay, considering uh, y and z as our constants. So when we differentiate this, with respect to x, we're going to have 8x y to the power 3, everything divided by z to the power 4. Okay. Then del u del y is equal to, we are differentiating y, u with respect to y, partially, taking x and z as our constant. So the derivative of y to the power 3 is 3y squared, right? But there is 4 here. So 3 by 4 is 12. So I've got 12 x to the power 2, y squared, everything to be divided by z to the power 4. Then del u, del z, will differentiate u partially with respect to z. So when we do that, we are going to have negative 16 x squared y to the power 3, everything divided by z to the power 5. I hope this is okay. You may be wondering why we are getting this. Of course, not everyone. We have this. Okay. If you want, you can write this as z to the power negative 4. So when you multiply this with that, you get negative 16, then minus 1 here. So we have what, x squared, y to the power 3, z negative 5. Okay, and you get what we have there. Okay. Okay, so we proceed. Now, Okay, so next. Now, we know that since this dx which are errors, maybe we recognize the errors since the errors dx is equal to dy, which is equal to dz, and this is fixed to be 0.0, I think 0.1. Yeah, from here. Okay. And these are positive, okay? These are all positive. We have du being equal to the first part, del u del x is 8x y to the power 3 divided by z to the power 4 dx plus del u del y is 12x squared y squared divided by z to the power 4 dy, the minus 16x squared y to the power 3 everything z to the power 5 dz. Okay, now for us to determine the percentage maximum error and get the maximum of du. So du max, so to get the maximum, we are going to introduce the absolute value. Okay, so it means we'll say the absolute value of xy to the power 3 divided by z to the power 4 dx plus, the aim is to ensure that we maintain the positive values. 12x squared y squared divided by z to the power 4 dy plus negative 16x squared y to the power 3 divided by z to the power 5 dz. Okay. So what does it mean? So to determine that, we are going to pick out the coefficients. So 8. But dx is a 0.001 plus 12. dy is a 0.001 plus here, because of the absolute value, so this thing becomes positive 0.001. Okay. And when you work out this with your calculator, okay, like this one, when you compute, what do you get? 8, open bracket, 0.001 plus 12, 0. The easiest is just to say 0.01, open bracket, 8 plus 12 plus 16. Okay, that is 20 plus 16, 36. Okay. So the answer is 0.36. This is our answer. All right. Now, this one that we found is the relative actually. So du max is uh is the is going to help us, in short, to find the relative error. Okay? It's not the final relative error. Because from the relative error or relative maximum error, we can determine the percentage maximum error. So we say, therefore, the the maximum percentage error, we can denote it by that, is equal to 0.36 divided by this original coefficient, which is a 4 here. We'll divide this by 4. Okay? This is what we get as our maximum relative error. And hence, our maximum percentage error will be equal to 0.36 divided by 4 times 100%. Okay. So just a matter of applying your calculator, 0.36. If you want, you can do it direct. You know that that will give you 36 divided by 4. All right. But I think here there's need of a correction here. It's supposed to be 0.001 open bracket times 36. Yeah, I think here there's need of a 0. We left out a 0 here. So even here, we put a 0 here. Okay. So what do we get finally? We get a 0.9%. Okay. That is our solution. That is how we get the percentage maximum error from a function. Okay, so first, you find the partial derivatives. From there, since we are talking about max, you also introduce the absolute values. Okay. Then where there is dx, dy, dz, you put the desired errors or the set errors. Then you work it out, provided you pick positive values. Basically, that's what you do. Okay, thanks so much. Till next time, please subscribe to our new channel, combined phiri-JM. Okay, and chaomba mbondo. Bondo. Okay, till next time. Bye bye, and God bless.